In this notes walkthrough, we'll learn how to simplify radicals using the product property and the quotient property, and we'll also learn how to rationalize the denominator. So the first thing we have to talk about is perfect squares. So perfect squares are going to be any number whose square root is an integer, so not a decimal. So if you know the square root of that number, it's going to be part of your perfect squares. So 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9, so on and so on. So I'm just going to go ahead and list some of the perfect squares that we have. 49, 64, 81, 100, 121, and 144. Now they go on forever. I could keep doing 13 squared, 14 squared, 15 squared, etc. But these numbers are going to be extremely important as we talk about simplifying radicals. The first thing for radical, and radical is a synonym for a square root, by the way. So radicals are going to be in simplest form when the number inside the radical has no perfect square factors. So what that's going to mean is when we have a square root, whatever number is in here, if a perfect square can divide this number, then it's not going to be in simplest form. If a perfect square can't divide this number, then it will be in simplest form. So if you think about a fraction just for a second, so the fraction 2/4, we all know is not in simplest form. But the reason it's not in simplest form is because you can divide top and bottom by 2, making it into 1/2. So if I had, let's say, the square root of 20, the way I would decide if that's in simplest form or not is I would see if 20 can be divided by any number on this list that I created. And the number that I'm going to ignore is 1, because 1 divides everything. So 20 can be divided by a number on this list. It can be divided by 4. Therefore, the square root of 20 is not simplified. And we're going to learn how to simplify it. But if I took, let's say, the square root of 10, so the square root of 10 can be divided by 2, 5, and 10. But none of those numbers show up on this list. They're not perfect squares, 2, 5, or 10. So it doesn't have any perfect square factors. So it is in simplest form. So it's simplified. So now we're actually going to figure out how we could take something like the square root of 20 and simplify it. So the first property that we're going to look at is the product property of radicals. And the product property says that if you have the square root of a times b, so if you have two things that are being multiplied within a radical, you're going to be allowed to split those things and give them each their own radical. This will allow us to simplify. Now the product property is actually going to work in both directions. So what that means is also that if you have the square root of a times the square root of b, you'd be allowed to put them underneath the same radical and multiply them. So the first thing we're going to focus on is the splitting of the product property, and then we'll focus on the putting back together of the product property. So for this first example, I have the square root of 32. So to see if 32 is simplified, I would look at my list of perfect squares, that was the 1, 4, 9, 16, 25, etc., and see if any number on that list can divide 32. If there's a number on that list that can divide 32, then it's not simplified. And there is a number on the list. 4 will divide 32. So since 4 will divide it, I know it's not simplified yet. But I want to see if there's actually anything bigger than 4. Because just like if you simplify, let's say, 20 over 40, if you divide top and bottom by 2, you're going to get 10 over 20. We're not simplified completely yet. I want to actually find the biggest number so I can simplify faster. So even though 4 divides 32, the biggest number on the list that will divide 32 is 16. So inside the radical, I'm going to rewrite 32 as a product of 16 times 2. So I'm still taking the square root of the same amount because 16 times 2 is still worth 32. I'm just splitting it up into a product. But now the product property that we just talked about said that if you're multiplying in a radical, which we are, we're allowed to split them. So I could make it the square root of 16 times the square root of 2. So now I have these two separate square roots. And I actually know the square root of 16. The square root of 16 is 4. So then I don't know the square root of 2, so I keep that. So my final answer would be 4 square root of 2. So this is the simplified version of square root of 32. They're the same. Just like over here, 1/2 would be the same as 20 over 40. It's just a simplified version. 4 square root of 2 is the same as square root of 32. I'm actually going to slide over to the square root of 24. So for the square root of 24, I want to find a number off of the perfect square list that will divide 24. And a lot of things divide 24. 24 can be divided by 8 and 3, but I don't know the square root of 8, and I don't know the square root of 3. They're not perfect squares, so I'm going to ignore them. 24 can also be divided by 2 and 12, so same thing. I don't know the square root of 2, and I don't know the square root of 12. They're not perfect squares, so I ignore them. But one set of numbers that can divide 24, 4 and 6, 4 is a perfect square, so that's the pair that I want to use. So instead of 24, I'm going to rewrite it as a product of 4 times 6. Then the product property lets me split them. So I can give each the 4 and the 6 their own radical. And then I know the square root of 4. The square root of 4 is 2. I don't know the square root of 6, so it stays inside, and I'm completely simplified. So you're going to pause the video and try this problem right here, the square root of 48. When you're ready to check your answer, press play. The hint that I'm going to give you for this problem is to make sure that you find the biggest number off the list that will divide 48. If you don't find the biggest number, you might do it correctly, but you might not completely simplify it. Pause the video, press play when you're ready to check your answer. So here's the absolute best way to simplify the square root of 48. The biggest number off the list that will divide 48 is 16. 16 times 3 is 48. And I can split them and give them each their own radical. And I know that the square root of 16 is 4. I don't know the square root of 3, so I leave it inside. So the final answer should be 4 square root of 3. Let's say by accident you found that 4 divides 48, and 4 is on the list, and it's 4 times 12. And then you split it into square root of 4 and square root of 12. You might have come up with this for an answer, 2 square root of 12. The problem with that is that 12 can be divided by a number on the list. 12 can be divided by 4, and 4 times 3 is 12. So I would have to resplit 12. Now the square root of 4 is 2, so this 2 would multiply this 2, give me an answer of 4, which leaves me the square root of 3. So you can see if you follow the blue or the red, you actually get the same answer. But it takes a lot more work to get there doing the red. Also, a lot of people tend to stop here and they think they're done, and they don't recognize that 12 can be split down farther. But just like you wouldn't leave 20 over 40 as 10 over 20, you would keep going. It's the same idea that 2 square root of 12 needs to be simplified more. Okay, so now we're going to focus on the problems that have variables and numbers. So in this problem, 9 and x squared are multiplying each other. So the product property tells me that I can split them into each have their own radical. And then I know that the square root of 9 is 3, and the square root of x squared is x. And the reason for that is because remember, like, for example, square root of 9 is 3, and the way that you prove it is you do 3 times 3 is 9. Same thing with x squared. It's got to be x, because x times itself would be x squared. So here the square root is 3, here the square root is x. So on the next one, if I do the same idea, I would split it into the square root of 25 and the square root of x squared, which would give me 5x. It is possible to do this just kind of in your head without actually showing this step. Even if you do it in your head and just get to the answer of 5x, you're still doing this step, but you're just doing it in your head. And so then on the last example, if I split them, so I have square root of 75 and the square root of x squared. So the difference this time is I don't know the square root of 75, but I can break that one down further into 25 and 3, and I still have the square root of x squared. So I know the square root of 25 is 5, I know the square root of x squared is x, and that leaves me with the square root of 3. And when you're writing your answers, the best way to write them is to go number, variable. If there's more than one variable, you do it in alphabetical order, and then one square root with however many things are left inside. So the product property actually works the other way as well, which tells you that if you have two things that are each inside of a radical and they're being multiplied, you're allowed to put them under the same radical and then multiply those things together. So in this case, it would be the square root of 6 times 6. But then the square root of 6 times 6 would be the square root of 36, and I know that the square root of 36 is 6. So this is a case where by multiplying together, I actually end up with something that I can simplify. If I I look at the one directly below, it would be the same idea. So it would be the square root of 7 times 7, which is the square root of 49. Then I know that the square root of 49 is 7. They won't always work out that nicely, but you still want to multiply and finish with one radical. So on this next example, what you're looking for is the items that are inside the radical. So here I have radical 3x, radical x. Because 3x and x are both inside the radical, I could put them under the same radical and multiply them. The 4, that's not inside a radical, would just come out. Now had there been something else, like say there was a number here that was also outside the radical, I'd be able to multiply those two numbers together. So if things are outside the radical, you can multiply. If things are inside the radical, you can multiply. I'm going to keep my 4, and then I'm actually going to multiply these, which will give me 3x squared. But now I can resplit. So we can make it radical 3 and radical x squared. But then I know the square root of x squared is x, so that will come out and join the 4, leaving me with only a 3 left inside the radical. So you're going to pause the video and try these 3 examples. When you're ready to check your answers, press play. So on this example, since 7xy squared and x are all inside the radical, I can multiply them together and put them under the same radical, getting me 7x squared y squared. The 3 that's outside will just come in front. Then I can split each of these, so they have their own radical each, and then I know the square root of x squared is x, and the square root of y squared is y, which leaves square root of 7 as the only one that I can't take the square root of, so it stays inside the radical. Here, since b and 2b to the third are all inside the radical, I can multiply them, giving me 2b to the fourth, and I can split them and give them each their own, and I know that the square root of b to the fourth is b squared. And the reason for that is because if we multiply b squared times itself, then you would end up with 4 b's multiplying itself, which is b to the fourth. So final answer, 3b squared radical 2. So I didn't know the square root of 2. And over here, since mn squared and 5 are all inside the radical, you can multiply them and put them under the same, but then you can resplit them. So I don't know the square root of 5, so that's going to stay inside. I do know the square root of m squared, which is m, and I do know the square root of n squared, which is n. So 2mn radical 5. So before we go on to the next part of this, we're going to go back to the first page where we talked about originally when radicals are in simplest form. So the first thing that we said was that the number inside of the radical has no perfect square factors, and that was why 20 was not simplified, because you could divide it by 4, which was a perfect square, but square root of 10 was simplified, because even though you can divide 10, none of the numbers you can divide it by are perfect squares. So the second thing that will have to happen in order for a radical to be in simplest form is there can't be a fraction under the radical. So what's going to be really important about this is it's not saying that you can't have a fraction, but what it's saying is that if you have a fraction, it can't be inside the radical. So you could not have, for example, the square root of 1/3. That would not be okay, because inside the radical is a fraction of 1/3. So just like the product property helped us simplify radicals, the quotient property will help us as well. So the quotient property works a lot like the product property. And what it says is that if you have the square root of a over b, so in this case, instead of a and b being multiplied like they were here, now a and b are being divided. Just like the product property, you're going to be able to give them each their own radical. We're just going to keep it dividing. So if you look, a was in the numerator, square root of a is the numerator. B was in the numerator, square root of b becomes the numerator. And just like the product property, the quotient property actually works both ways as well. So there are times when it may make sense if you have square root of a divided by the square root of b, it might make sense to put them under the same radical. So on the next slide, we're going to see this in action. So on this first example, we have the square root of 16/25, and because it's a fraction, we're not allowed to keep it like that. We have to split it up. So the quotient property tells me that I can make it the square root of 16 divided by the square root of 25. Well, I know the square root of 16 is 4, and I know the square root of 25 is 5. So this one actually worked out very nicely. So if I come over here to the next one, inside this radical I have a fraction, it's 13/100. So I'm going to make it the square root of 13 over the square root of 100. I know the square root of 100 is 10. I don't know the square root of 13, so that one would stay inside the radical. So if you look, I have a fraction, but what I don't have is a fraction in the radical. So the fraction is okay, but inside the radical is just 13, and 13 by itself isn't a fraction, so I'm in good shape. So you're going to pause the video, try the next 3 examples, press play when you're ready to check your answer. So in this first example, because it's a fraction inside, I can split them each, make it square root of 1 over square root of y squared. Square root of y squared is y, and then don't forget that the square root of 1 is just 1. A lot of people forget that one. On the second example, I can split it so it's the square root of 5 over the square root of 49, but I know the square root of 49 is 7. I don't know the square root of 5, so that's my answer. So even though my answer is a fraction, inside the radical I only have 5, which is not a fraction, so I'm okay. And on the last example, I split it into the square root of 11 over the square root of the d to the 4th. And the square root of the d to the 4th is d squared, and the square root of 11 I don't know, so it stays inside the radical. So there's a third criteria in order for radicals to be simplified, and that's that if you have a fraction, you can't have a radical in the denominator. So on all of the previous examples where we ended up with fractions, we had the radical in the numerator, so it was like square root of 2 over 5. So that's fine, because even though it's a fraction, there's not a fraction inside the radical, and there's no radical in the denominator. What wouldn't be allowed is if you had like 2 over the square root of 5. That would not be allowed, because there's a radical in the denominator. The reason for that is because if the radical is in the denominator, that means you can't simplify it. Because if you could, you would. And so that's going to be an irrational number. And so mathematicians decided that they didn't like when the fraction of a denominator of a fraction was an irrational number. So we're going to have to change that to a rational number. And that's the next thing that we're going to work on doing. So for this last part of the notes, if you look at each denominator, they're all a radical that can't be simplified any more than it already is. So every denominator is currently irrational. I want to make it rational. So the problem in this fraction is that in the denominator is the square root of 7. So I want to cancel out a square root of 7. Well, remember that the inverse of square rooting is to square something. Those are the 2 operations that cancel. And to square something, if you want to do like x squared, you multiply x by itself. If you want to do 3 squared, you multiply 3 by itself. So anytime you want to square something, you multiply it by itself. In this case, the thing that I want to multiply by itself is the square root of 7. So I'm going to take the denominator of this fraction, and I'm going to square it, which means I'm going to multiply it by its exact self, which is the square root of 7. Now the reason this works is because 7 and 7 are both inside the radical, then I'm allowed to multiply them. So I would be taking the square root of 49, but then the square root of 49 is 7. So I've taken what was originally an irrational denominator, and I've made it into a rational denominator. 7 is a rational number. But with fractions, the golden rule is that whatever you do to the bottom, you must also do to the top. So I also need to multiply the top by the square root of 7. Since 5 is outside the radical and 7 is inside the radical, I can't actually multiply them together. So the best that I can do is show that I want to multiply them by making it 5 radical 7. So the numerator of my fraction is 5 radical 7, and the denominator is 7. Now since the 7 on the top is inside, and the 7 on the bottom is outside, I cannot divide them. You can only multiply or divide if both items are either inside or outside the radical. So in this case, 5 and 7 are both outside, but that fraction is already reduced. But if it wasn't, we would actually be able to reduce it. So let's do one more of these. So on this problem, I have a fraction, and the problem is that it has a radical in the denominator. So I want to cancel out a radical 3. And to cancel out square root, I square, which means to multiply by itself. So I'm going to multiply radical 3 by its exact self, which is radical 3. Then whatever I do to the bottom, I also have to do to the top. So now the square root of 3 times the square root of 3 would be the square root of 9, but I know that the square root of 9 is 3. So I went from an irrational denominator to a rational one. On the top, since 2 and 3 are both inside the radical, I'm actually allowed to multiply them and make it the square root of 6. So my numerator is the square root of 6, which can't be simplified anymore because no perfect squares will divide 6. And since 6 and 3, since 6 is inside and 3 is outside, I can't divide them. That's your final answer. So you are going to try the next 5. Pause the video. Press play when you're ready to check your answers. So on this example, I want to cancel out the square root of 3, so I'm going to multiply it by its exact self, but then I also need to do it to the top. Square root of 3 times the square root of 3 is technically the square root of 9, but I just made a shortcut and made that 3. And then on the top, 1 times the square root of 3, 1 times anything is itself, so just be square root of 3. If you have a 1 in front, that's fine as well. On the next example, I'm trying to cancel out square root of x, so I multiply it by itself. Square root of x times the square root of x would be the square root of x squared, which is x. 1 times the square root of x would just be the square root of x. Again, if you have a 1 in front, that's also fine. Here I'm going to multiply top and bottom by square root of 2, because that's what I'm trying to cancel. Square root of 2 times the square root of 2 is the square root of 4, which is 2. 3 is outside, 2 is inside the radical, so the best I can do is show that I want to multiply them without actually multiplying them. Here I multiply top and bottom by radical 6. Square root of 6 times square root of 6 would be square root of 36, which is 6. And then on the top I end up with 7 radical 6. And for the last example, I multiply top and bottom by radical 5, because that's what I'm trying to cancel. Radical 3 times radical 5. Since they're both inside the radical, I can multiply them to get radical 15. Square root of 5 times square root of 5 would be square root of 25, which is 5. 15 has no perfect factors, so it's in simplest form.